Okay, hello everyone. So in this lecture series, we are going to look into control design, okay, control system design for electrical networks. So when we say electrical network, so we have some passive components in the system like resistance, inductance, capacitance, and some active components in the system such as voltage source or a current source, or there can be some dependent sources, some non-linear elements like power electronic devices, diode, IGBT, and all those things. So in electrical network, we are interested in achieving some performance out of that electrical system. So when we say performance, we mean either voltage or current, or we want to achieve a certain power, or we want to achieve a certain kind of energy, and we want a certain dynamic performance out of that circuit, like my voltage should reach a certain value in say 1 second duration, okay, or the oscillation happening in the electrical network should be damped out. So those kinds of objective we have in terms of voltage, current, and its functions. So its functions are basically power, energy, or its function can be like charge or current. Sorry, charge or the flux, and all those things. Okay. Now, when we say control system design, so what do we mean exactly? So there are, as we know, there are definitely the passive components, which are basically hardware component. We cannot do anything about it. So whatever they are designed, they are what they are. So a resistance designed for say 10 ohm will be 10 ohm plus or minus some tolerance. So that is fixed once it is designed, and it varies probably based on some environmental factors like temperature, pressure, and aging, and all those things. So, but resistance is almost fixed, whatever value it is designed for. Similarly, the case for inductance and capacitance. Okay, so what drives the electrical network is basically active sources, which are basically voltage source and or current source. So when we want to control the voltage and current and their functions in a electrical circuit, then we are basically controlling the active sources. So we are designing a kind of controlled current source or a controlled voltage source. Okay, that is our main objective here. Yeah. So basically, what steps we take when we go for control system design is basically we should define the problem. So basically, how do we define the problem? We specify what do we want out of that control system, what do we want from the electrical network. So we first define the objective. What is our objective? What is the control objective, right? Then we see in our system, given that objective, is it feasible? Is it feasible means, is there any limitation in achieving that objective? So we also look at some constraints of the system. So constraint in the sense, we cannot ask an electrical circuit to produce infinite amount of power, or say we cannot ask for a very high short circuit current which can damage the equipment. So we have to limit the current, limit the voltage to the equipment ratings, right? For some duration we can overload, but not for the steady state duration. We need to respect their steady state limit and dynamic limits. So there are system constraints always there in the system. Okay. Now, given the objective and knowing the system constraints, we go for the process of design. And the first part is to model the system. Okay, so we should have a system model available with us. Model means the mathematical representation of exact physical circuit. So mathematically, we can have model in the form of time domain differential equation of the system, right? Like suppose simple resistance connected to voltage source. So system model is simply V equal to IR. So that is the Ohm's law. Similarly, if it is an inductor, then voltage across inductor is basically L di by dt. So That mathematical representation is basically the model. So it can be in the form of time domain equation, it can be in the form of a phasor equation, it can be also in the form of a Laplace domain equation. Okay, so model has to be there, some mathematical description of the system has to be there, and then we start our process of designing the control system. So that design comes later when we have objectives, constraints, and model of the system readily available with us. So that is these are the basic steps in carrying out the control system design and achieving the performance whatever is we want from the out of the system. Okay, so I am assuming that all of you are familiar with basic network theory, basic fundamental laws of electricity, and network theorems like Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law. These are the fundamental laws of electricity, and the network theorems. Network theorems include like basic superposition, Thevenin, Norton, and basically all those things. So apart from that, I am assuming that you have the background knowledge of basic control system. So you know what is open loop system, closed loop system, and you have at least some idea about state space and frequency domain analysis of the systems. Okay, so control system not much required. We will cover that in in this lecture series, and we will start with very simple electrical networks like RL circuit or RC circuit and RLC circuit, and we will define our objective, define the system constraint, and model the system, and we will see how all these things impact on the control design and how we can achieve a particular performance from the system. Now we are designing it for very simple RC circuit. It does not mean that it is not applicable to any other system. So even if we take a large complicated systems, like say complicated multi-level converters or power electronic circuits and large power system networks, so the principles are remains the same, and those principles are applicable. Only the dimensionality of the system increases. So there is nothing new when dimensionality increases, just we need some readjustment and refining the model, so that model will be simplified and simplified design will be carried out. So basics should start from a very simple circuit like simple RL and RC circuit, and then the same principle will be applied for a very complicated electrical network like large power systems or complicated power electronic circuits. Okay, so with this note, let us start our discussion on a simple circuit, say RC circuit. Okay, so what is RC circuit here? We are just collecting some parameters, right? So system has some passive components like resistance and capacitance, and we are basically trying to achieve some performance out of this electrical circuit. So uh, when a passive network will not do anything, we need some active component and some uh, active live electricity flowing into that network. So let us define some parameters such as the voltage on the capacitor. Say this is denoted by VO. Let us call that as an output side, and voltage on the input side, say V in. Okay, and of course the current some I current will flow through the circuit, and this is the circuit. And now let us define our objective, because without objective there is nothing. The first step always is to clearly define and mathematically express the objective. So we suppose we want the voltage on the output side should go to V reference, some value. Say for example 10 volt. So we want that output voltage should be equal to 10 volt. That is our objective. Okay. Now, how do we achieve that objective? Because we need someone to control that. Okay. Someone to make sure that 10 volt will be achievable there. So what is our control input in this case? So control input is let us say V in. Okay, so try to understand the problem. We have a V in which is kind of controllable. Suppose we want to design the V in such a way that output voltage is equal to reference value, which is 10 volt in this case, and given the R and C value. So we know the system, we know the system parameter, which is R and C, and we want V naught in to track this V reference value, and we will with the control channel or control input available with us is V in. Okay, so that is basically the objective. Now, suppose if I want to put some constraint, so I can put a constraint, okay, a constraint on the system such that, say, the current flowing through the system or flowing through this resistance, and it will also flow through capacitance. So this should be limited by its maximum value. Okay, so this is a kind of constraint, say maximum value, say we don't know, say 1 ampere, whatever. Okay, so it should not exceed 1 ampere. So we need to ensure that also. That is a system constraint. So after defining objective and after knowing the system constraints, now the task is to mathematically describe the behavior of this circuit. Okay, so how do you describe it? So there are multiple ways of describing the circuit. Let us see the Laplace. Let us do it by Laplace way. Okay, so we have a resistance and a capacitance here in the shunt, and we have a V in on the input side, and output side we want to achieve a certain voltage equal to V reference. Okay, that we want to achieve, and this is the circuit, right? Okay, in Laplace domain, we write this circuit as, I hope all of you know the Laplace transform, and the capacitance in the Laplace domain becomes 1 upon Cs, right? So this is the V naught, and this is V in this case, right? And now we want to define the mathematical representation of this circuit. So we have these parameter R, C, V naught, and V in, and we will now describe how they are mathematically related, right? So let us consider that circuit and just derive it. So we have R, C, and V in here, V not there, and say current I is flowing there, and same current will flow here, I. Okay, so in Laplace, C becomes 1 upon Cs or 1 upon Sc. Fine. Okay, now let us write the equations. Okay, V naught is basically the impedance, which is 1 upon Cs multiplied by current. Now input voltage V in, looking from the circuit by applying simple Kirchhoff's voltage law on the circuit, it is basically the drop across the resistance plus the voltage drop across the capacitance, right? So this is, I can take current as a common, and this becomes R plus 1 upon Cs. And now let us define this ratio, output voltage to the input voltage. Okay, so this divided by this, so you can see the I current get cancelled, and in the denominator we have 1 upon Cs, and in the numerator we have 1 by Cs, denominator 1 by R plus 1 by Cs, and that can be simplified and obtained as 1 upon RCS plus 1. You can verify that later. Okay, so let us define it as 1 upon tau s plus 1, tau s plus 1, where tau is basically defined as R into C for that circuit. Okay, so now what we are doing, we are basically deriving a relationship between output voltage and input voltage in the form of this ratio, and this is basically transfer function between output and input. So this is basically a transfer function, right? And this is the circuit. This is what we want to control. This is given to us. This is given means we cannot modify anything about the system. The system is given as it is. Like tau, we cannot really control in the hardware component. We cannot change. So basically we want to vary V in and we want to achieve the V naught to be equal to V naught reference or V reference, whatever reference value. Okay, so that is our objective and this is what we want to achieve. So this is the mathematical model of the system that we are trying to control. Okay, so I hope this can be understood very easily if you have the background in basic of Laplace transform circuit analysis. Okay, so going ahead, in the next video, probably we will discuss how to design this control, how many ways are there to design this, what are the limitation or pros and cons of each method and all these things. So for now, let us take a break here and thank you.